So let's welcome Vitalik here to Singapore once again. Thank you.
Next. So today what I'll be talking about is start off with a brief introduction to the progress that Ethereum has made over the last few months, but then I'll zoom in particularly on one of the interesting features of Ethereum 2.0 that's going to come here once we have a smart contracts and state execution, which is this concept of account abstraction, and some of the interesting consequences and interesting things that you'll be able to do with that. So to kind of put everyone on the same page, this is the kind of Ethereum roadmap, 2.0 roadmap in one slide diagram. So the Ethereum's proof of stake and sharding plans are split into these 4 major phases, where phase 0 is what's called the beacon chain, which is just this proof of stake chain. And for phase 0, the spec continues to be almost complete and continues to be in kind of error checking, debugging, and simplifying mode. The size of the spec has actually decreased by over 10% over the last couple of weeks. Over the last couple of weeks, one major piece of good news is that Ethereum 2.0 client implementers have been announcing testnets for phase 0. So you can go to the Lighthouse page and you can run a node and join the Lighthouse testnet. And sorry, no, it's the Nimbus testnet. I mean, Lighthouse and Prismatic and others are also in the process of releasing things very soon. So yay! So after phase 0, we have phase 1, which is where the sharding part of sharding comes in. And here, basically, we have the 1024 shard chains turn on, but the shard chains are not going to be completely active. Instead, they'll begin by just being a kind of relatively dumb data layer, and on that data layer, you'll be able to just throw whatever stuff you want, and it's about, at least given the numbers we're thinking about, somewhere close to 5 megabytes per second of kind of consensus guaranteed data availability, but that data by itself doesn't mean anything. Now, that just a pure data layer is useful for a lot of applications, and I gave a presentation, actually the same presentation twice, once in Taipei, once in Korea, where I talk about applications that you can do just using a scalable data layer. And basically, there's something called ZK rollup that you can do, where you use ZK snarks on the ETH1 chain with pointers to data guaranteed by the ETH2 chain, and you can get many thousands of transactions per second. Right? So these are things that will become available fairly soon. Phase 2 is when the system is kind of technically fully mature, which is when it's not, the shards are running, and they're not just running data, but they're also actually processing smart contracts, executing code, maintaining state, maintaining accounts, and all of these other things. So today I'll be talking about abstraction, and abstraction is something that we've talked about in the context of Ethereum for a long time, but it's going to be a major feature of this. And phase 3 starts and further Casper CBC, other fun features. That's something that's going to come later, but there was already specs for example, Casper CBC, and there's teams that are looking to kind of formally verify different versions of CBC, so this is well on its way. And for phase 1, the spec is relatively close to done as well, but it hasn't really been started being implemented. So what do we mean by this weird and magic word abstraction, right? So basically, the idea here is to, well, we can define abstraction by looking at it in terms of things that it's not, right? So who here has watched me introduce Ethereum and talk about how before Ethereum you had these kind of some pocket calculator blockchains. It's Swiss-Army-knife blockchains where you define 10 different features and that's all you can do, but Ethereum is much more powerful because you have a programming language. Okay, so basically that is an example of abstraction, right? And that's the application logic. That's a kind of abstraction that Ethereum already has, and it's a kind of abstraction that basically is what makes the blockchain so powerful. But really, this kind of concept that instead of defining specific ways of doing things in protocol, we just make the protocol maximally open to doing whatever you want and letting more things be defined at higher layers is something that can be extended to other aspects of the protocol as well, right? So for example, tokens, you can argue that they're kind of semi-abstracted because whereas, say, in Bitcoin, there's only one token that you can use. In Ethereum, well, there's ETH, which is kind of a privileged token, so it's not fully abstracted, but you can make your own tokens. You can have applications that that use your own tokens for payment. You can do lots of things. Signature verification. So today, signature verification is not abstracted. And when something is not abstracted, we often call it, quote, enshrined. So basically, there's these two kinds of accounts. One kind of an account is this externally owned account, where it uses a very particular digital signature scheme called ECDSA to verify transactions. And if you want to use something else, as I'll show you soon, you have to go through a lot of pain. And we want to basically replace this with a scheme that says you can use whatever signature verification scheme you want, and it's kind of just as easy as it is today. Replay protection. So to prevent a transaction that's valid from being included twice, currently we use this very specific scheme involving nonces, where every transaction has to include a number that keeps on going up. But this is something that we can kind of abstract away and leave as a responsibility to the user as well. Transaction fee payment mechanisms, they're currently kind of enshrined now in the form of the gas and gas price fields by transaction. And we can abstract those and give the user the choice and the responsibility to figure that out as well. So what are the goals of all this, right? One of the goals is consensus layer simplification. We want to reduce the number of lines of code, lines of whatever in the consensus layer that all nodes have to agree on, because that's code that has to be written many times, it has to be tested a lot, it has to be audited, and if it breaks, the protocol breaks. So we want to shrink it. Increasing flexibility or freedom or optionality for users. You as a user should not be stuck with one way of doing things. You should be able to kind of upgrade to your own way of doing things on your own schedule. Quantum security. So with abstraction, upgrading to quantum secure algorithms becomes easier because each individual user will be able to upgrade on their own schedule instead of having to coordinate a hard fork with one flag day where everyone is forced to upgrade at the same time. So signature abstraction, right? So today, the top bar is what we have today. So in a signature scheme, you basically have these four components: private key, verification data, or public key, signature, and a verification algorithm. So your private key today is a 32-byte number. Yay! Your public key or verification data is your address, which is 20 bytes. Yay! Now the signature is these two values, R and S, that are each 32 bytes. And the verification algorithm basically just says that you do the CC recover operation on the signature and on the message hash. You recover an elliptic curve point hash and take the last 20 bytes and check that it matches your address, right? So that's how it is today. Now here's how we might want to do it tomorrow, right? So private key could be anything, depends on the algorithm. Public key, your public key is now a piece of code. Your signature is now a piece of arbitrary data. And the verification algorithm is you just execute the code using the data with the message hash prepended as an input. So if you personally want to keep using ECDSA, you would just have to write a piece of verification code that says, hey, run this exact map that I put up in this top right square and do this exact same check that we were doing before. But you don't have to use ECDSA. You could use ECDSA multisigs, you could use Schnorr, you could use BLS. If you want quantum proofness, you can use Lamport. You can do all sorts of crazy stuff. So to give a concrete example of how this improves things, this chart on the left is how you have to do a multisig today, right? So if anyone's used a multisig, who here uses a multisig to hold their money? Not specifically in Ethereum. Yep, okay, that's pretty good. But the reason why not more people are doing it, a big part of it is just because it's annoying and hard, right? So here is what a multisig looks like from a kind of code point of view. Your transaction goes into an account, and it has to be this special type of account called an externally owned account, which is not a multisig. It goes into that account. Then that account itself makes a call to the multisig contract, and then that call itself contains signatures from other public keys that need to be verified. The multisig contract verifies those signatures, and it passes on the call to the recipient, and then it sends some keys back to the account, or possibly you have to do it yourself to make sure that this account continues to have enough ether inside of it to pay for gas. So, who here agrees that this looks needlessly complicated? Well, it is. So here is what multisigs will look like after abstraction. Who here agrees that this is simpler? Okay. So signature abstraction, right? This is actually pretty simple to implement, and it's by itself, it's a very high value kind of abstraction. So the main restrictions here is that we need a gas limit on execution. So, and this can be basically to prevent miners or block proposers that receive a transaction from having to just run a huge amount of computation and not know whether or not it'll even give an answer at the end. And the execution needs to be a pure function, right? So signature verification cannot be state dependent. So one challenge here also is that in ECDSA, like this verification data, the public key that we're talking about is really tiny, so we just use it as your address. But here, the verification code might need to be stored separately. And so we would basically need to have extra logic that says, if the verification data has not yet been published, it has to be published in the first transaction. So that's signature abstraction. But we can go even further, right? We can go to full transaction abstraction. So in full transaction abstraction, the core idea here is that a transaction is just a function call, right? So the kind of logic for processing a transaction and the logic for processing what's called a contract call today can just be exactly identical to each other. The only difference is that with a transaction, the sender is some standard dummy address like the number -1 that just represents that it's coming from the outside. Now, what's difficult about this, right? There's 3 challenges that we need to solve here. One of them is kind of block proposer DOS resistance. So this basically says, if you are a block proposer and you're thinking about whether or not to include a transaction in a block, there needs to be some procedure you can quickly run to determine whether or not the transaction will pay fees. Currently, that procedure is simple, right? You basically just check the signature, check the nonce, check that the account has enough money, and you know that regardless of what the execution will be at the end, the thing still pays its gas. So with abstraction, but with the dumb way, that's not solved. Network DOS resistance. So how do nodes on the network, on the peer-to-peer network, determine whether or not to relay a transaction? And what you want is for them to only relay a transaction if they determine that the transaction actually has some significant chance of having to pay a fee. So you don't want relaying to be costless. And you don't want spamming the network with transactions that will be relayed to be costless. And the third problem that you have is basically that if you abstract everything, then there's no rule anymore that makes it illegal to just have the same transaction appear in a block 5 times. And so you'll need some new kind of transaction identifier, some replacement for transaction hashes. So let's think about this more concretely, right? What will this look like? Yay, code. So this is an example of roughly what a piece of account code might look like for an account or for a contract that is representing a user account, right? So basically what we're going to do is this is a piece of code, and it's going to interpret it has access to the body of the transaction, and it's going to interpret it as an object that has a bunch of parameters. So it's going to just treat this as an object and deserialize it into this class. And now we're just going to do a bunch of checks, right? So it's going to interpret, say, the first 8 bytes of the transaction as a nonce. and it's going to check that it equals the nonce in the storage. It's going to interpret part of the transaction as a signature, and it's going to check that the signature of the transaction is valid. Then it's going to send the fee to the proposer. Then the nonce is going to go up by 1, and then the transaction will just kind of pass along the call that it was meant to do. Right? So basically what we're doing here is we're taking the logic that already exists currently kind of enshrined in the Ethereum 1.0 protocol, except in Ethereum 2.0 we can just move it inside of accounts. Who here is following along so far? Okay. So this is good. I see nothing, right? So abstraction basically says you take a lot kind of code software logic that's currently part of the protocol rules, and instead you just make the protocol rules much more on a general purpose. And so instead, like, that logic still has to live somewhere, but then users just implement it in some, or like, realistically, kind of software developers writing software that users use implement it themselves at higher layers to implement the same functionality in a more kind of voluntary and modular way. Now, you might notice here, this is, what's on the left is basically what a transaction looks like from the point of view of the consensus layer, right? So from the point of view of the consensus layer, a transaction actually needs fewer parameters than it does now, because the parameters are no longer kind of enshrined in the protocol, right? Instead, the parameters live at this lower level that's just voluntarily decided by individual accounts. So what the consensus layer sees is just 3 data fields. Now, the serialization algorithm that we're using for Ethereum 2.0 has this really wonderful property that if you don't fully know the structure of an object that you're dealing with, then you can just treat the parts that you don't know as just being bytes. But then if you do know the structure, then you can also just interpret it as an object where all of that actually kind of expands out into what its parameters are, right? So from the point of view of the consensus layer, it just sees this, and the consensus layer doesn't care what's in the body. From the point of view of code in the account that's being executed, then it actually does kind of decompose the body into these parameters that we saw, and it does kind of interpret them in its own specific way. Now, different accounts can have different logic. They might have these things in different orders, but what matters, basically, it's the same sort of stuff that was kind of forced to be done the same way by everyone now can be done different ways by different users. So now let's talk about safety a little bit, right? So what I just showed is not very safe for block proposers, basically because a block proposer has no way of verifying before it runs through the complete transaction that the transaction actually is going to pay the gas and that it's not going to revert at the end and just end up not paying a fee at all. So here's one proposed approach. We add this opcode called breakpoint, and the breakpoint opcode just has one rule that says if a transaction exits with an error after a breakpoint, then it just reverts to the last breakpoint. And so now what we do is we just say after the logic in the transaction, that the very small piece of logic that just verifies the signature and the nonce, we set a breakpoint. And so if anything, regardless of what happens after that, even if it reverts, it'll only revert back to the breakpoint. And so after that point, there's no way to kind of stop the payment from happening. And so a block proposer can just execute the transaction, and if it sees a payment and then it sees a breakpoint after the payment, it knows that that transaction is going to pay them the money they deserve, and so they can just include it and fully execute it, and they know they're not going to get dust. So now the main challenges that we have is this doesn't solve network layer problems, and we don't have a notion of gas refunds at the end, right? So if your transaction uses some uncertain amount of gas, it still just has to pay for the maximum, it doesn't get refunded. So network layer issues. Network nodes can get dust too, right? And the problem with a network node is basically that network nodes need to be sure that a transaction is costly, that a transaction has some chance of being included in a block and having to pay a fee, like basically regardless of what block it gets included in, because otherwise you can just do weird attacks and you can spam the network with transactions that look valid but actually stand no chance of actually costing the sender anything. So there's a kind of multi-part solution to this. One of them is to add this pay gas opcode that basically is an explicit opcode for just paying the transaction fee to whoever the block proposer is. And we can just, in this pay gas opcode, we can just throw in logic for refunding gas at the end. Right? So that solves two problems at once. So that basically means that instead we have this mechanism where you can actually check for the pay gas opcode and you can make sure that whoever the block proposer is, they'll get paid. Network nodes can also do some additional checks. So they can basically check that a transaction will not access external state, that it's not going to access the environment, that the account itself doesn't let external things access it except for sending an ether. And so if you do that, then you have this invariant that basically says, if I see a transaction, then, and to me right now, it looks like that transaction is going to get in and it's going to pay fees, then I know for a fact that that transaction will keep being valid and will keep paying me fees until or unless either that transaction or some other transaction from the same account gets included. So we can add kind of some more structure, and basically there's a trade-off here, right? The more structure we add, the more, and the more structure we kind of enforce at the network level, the more guarantees that we can get. And the less structure we have, the more optionality there is, but the more difficult it is. Right? So the strength here is that the abstraction model remains super simple. There is some more complexity, but it's kind of at the network layer rather than being at the consensus layer. So let's talk about one very specific use case of abstraction, right? Mixers. Yay, who here finds mixers more fun than looking at code? Okay, so mixers in theory, right? So you have a smart contract, and people are using it to anonymize their coins, right? You have a bunch of people sending coins in, and then you have people providing proofs, and they get their coins out, and you're not supposed to tell which input corresponds to which output. Yay, you're anonymous. Now let's look at reality, right? So this is what happens if you try to implement a mixer on Ethereum. Let's say I have some money, and I'm going to try to mix it. So I'm going to send my money into the mixer contract. Now, how do I get it out? Well, to get the money out, I need to send a proof into the contract. To send a proof into the contract, I need to send a transaction. To send a transaction, I need to already have transaction fees that get charged in an enshrined way in the protocol. To do that, I need to have some money. Let me send myself some money. Oh wait, I de-anonymized myself. So abstraction can solve this, right? So basically, with abstraction, we can just have logic that says, instead of the fee being paid through this enshrined mechanism, the mixer contract itself pays the fee after it figures out that the proof is legitimate. And so you can do the proof checking first if it's fast enough, and then you pay the fee afterward, and you're all good, and you don't have this data leak. Yay, more privacy. So transaction IDs, this is kind of the last issue, right? So basically, notice that in the mixer use case, we've kind of introduced a new way of using accounts, right? We've basically introduced this new use case that says, instead of a top-level account representing either a user, it's one of these accounts that get access directly from outside the system represents multiple users, and the users might want to do withdrawals in parallel, and so you can't kind of enforce a common non-scheme because if different users are coming in and trying to withdraw in parallel, they have no idea which one of them is going to come first, which one of them is going to come in which order. So basically, because of this, we can't have kind of enforced in protocol nonsense, and so because of this, we have this problem that it might be possible for a transaction that has the same hash to be included multiple times. So here's the problem. This is obviously annoying, right? We're kind of used to going to etherscan.io/tx/whatever our client gives us and just refreshing the page over and over again until we see the transaction confirmed, right? Who here has done that? So we want people to be able to keep spamming an Etherscan page over and over again because it's like a pretty user-friendly workflow compared to other things. So the problem is, well, here one transaction might correspond to 10 different, or one transaction hash might correspond to 10 different transactions. And when you send a transaction, the transaction could potentially be modified in transit because we're not enforcing what the signature scheme is, and so you might choose a signature scheme that lets other people modify your transaction in transit. So here's the proposal, right? Instead of having this transaction-centric workflow, we can try to have a receipt-centric workflow. And the receipt-centric workflow basically says, when you create a transaction, instead of just generating the transaction hash, you generate an ID or possibly a list of kind of event IDs that represent the kind of hash of things that you want to have happen actually happen. And then when a transaction gets executed, it makes a log, and that log publishes a receipt ID. And so instead of spamming Etherscan for a transaction hash, you would just spam Etherscan for a receipt ID. So now it just keeps on working very similarly, except it works the same way, even if you have one transaction included multiple times, or your transaction gets modified in transit. So hibernation and waking, there's this is the mechanism for kind of how rent in Ethereum 2.0 works. Basically, one of the annoyances of waking, right, is that let's suppose you have an account, and then you receive some tokens. Then your account is forced to go to sleep because you haven't paid rent. Then, while your account is asleep, that same account receives more tokens, and then it pops into existence again. And so we have some tokens over here and some tokens over here. What am I going to do? So basically, to resolve this problem, well, we need to start thinking about either we forbid sending to accounts that don't exist yet, or we have some kind of abstracted notion of merging that contracts have to specify. So this is just kind of some of the examples of challenges that that abstraction involves. But I mean, hopefully, as you can see, right, this creates a really extremely powerful set of possibilities, right? It basically means multi-sigs can be as easy to use as single-sig accounts. Yay, security. It means that you can finally have mixers that work. Yay, privacy. You can have Lamport signatures. Yay, quantum proofness. So we can have lots of, you can even have a UTXO system be built on top of this. Yay, being more like Bitcoin. So, right, this is the power of abstraction. You can be whatever you want to be. Now, how do we make this efficient, right? So basically, instead of 10 lines of code, or 10 to 50, whatever number of lines of code being in one place in a piece of in your client software, basically all of that code ends up going into accounts, and those accounts get copied over 1 million times. So space-wise, this seems less efficient. So how do we make this efficient? So this is one problem, and then the other problem is interpretation efficiency. Is basically, instead of these pieces of code being optimized code, they just become virtual machine code, which might need to be interpreted, and interpretation has about a factor of 100 overhead. So how do we solve the space efficiency and the complexity efficiency issue, right? So a solution that we're seriously considering for this is this kind of make-your-own precompile approach. And the make-your-own precompile approach basically relies on this idea that for WebAssembly, which is the VM the virtual machine we're replacing the EVM with in Serenity, WebAssembly code can be executed either with an interpreter, which means you can just grab any code and immediately execute it, or a compiler, which requires a lot of pre-processing time. But once you're done compiling, you can just execute that code, and on average, it's about 90 times faster. Probably actually very close to native code, possibly less than a factor of 2 overhead over native code. So here's the idea. On the beacon chain, so on the proof-of-stake chain, the central chain of the system that every user has to keep track of, you can pay 1 ETH. And if you pay 1 ETH, you have the right to push a pure WebAssembly function, a pure piece of code, and everyone is required to compile it, and anyone in every shard can kind of just call this like they call a precompile today. So this becomes just one of these special functions that you can call. So now we have a way of doing libraries that's really efficient. we have a way of basically making your own precompile that's really efficient. And you can use this to store account code, you can use this to store cryptographic verification code, you can use this to store a whole bunch of things, right? So basically you can just make accounts themselves just be, hey, point to this thing, except here is the kind of 32 bytes that actually are my particular cryptographic key, and you have about as much space efficiency as you had before. Yay. Economic abstraction. So this is the kind of last thing I want to talk about. There's this common desire to kind of let people pay for transaction fees in tokens if block proposers accept them. So let's say, for example, you are some token issuer. I don't know. Let's say you're trying to issue digitized Vietnamese dong, and you want to have and you're just sending this as an ERC20 to people in their wallets, and you want people to be able to send this to each other, but you don't want to also have to deal with the user experience headaches of having to give everyone ETH and forcing everyone to keep a balance of ETH, right? So an idea that people have brought up is this concept of kind of, quote, abstracting Ethereum and basically making the platform currency neutral, and basically letting people pay fees in whatever currencies anyone accepts. I would argue this is a very bad idea, and it's a bad idea for a few reasons, right? So one of them is that it just makes DOS resistance harder because it basically requires some form of governance to determine kind of which coins are actually legit, which coins are actually worth something. You then have to do this really ugly thing where you have the peer-to-peer network layer kind of poke into Uniswap and ask Uniswap what the exchange rate between your Vietnamese dong ERC20 and Ethereum is. So it just gets really complicated. Also, the Ethereum platform depends on the value of ETH specifically to ensure proof-of-stake network security. Finally, transaction fees that are not going to a block proposer, but transaction fees that are going kind of directly to the protocol. So this would include the 1 ETH you pay for precompiles. It would include the base fee from EIP 1559. It would include storage rent. All of these fees that don't go to anyone, that just get destroyed, have to be charged in some standard currency. And the pay gas approach that I talked about can't be extended to tokens easily, right? So we can't it turns out that abstracting away kind of Ether as a currency introduces way more problems than it solves. But how can we give people what we want anyway, right? So auto poke mechanism. So here's the idea, right? So first of all, if we add EIP 1559, which is this wonderful transaction fee market reform proposal that I'm going to be presenting about at the Magicians meeting in a few days, then you have a kind of reliable in-protocol feed of what the current gas price is. And so you can tell inside of the protocol whether or not an account has enough ETH to send one transaction. Now we have a poking mechanism. And a poking mechanism basically says, if your account has not enough ETH to send one transaction, then you authorize anyone just anywhere to poke the account, and that just means send a transaction targeting that account that just basically automatically calls Uniswap and converts some of their tokens into Ether, just enough so that they now have enough Ether to send one transaction. And whoever pokes this get a reward. Account abstraction makes poking really cheap because poking transactions don't need to have a signature, so it's literally just like 20, 30 bytes, that potentially even less, that you would just throw into a block and it would just get processed, right? So let me just skip over some of these more the last section. So basically, we don't need economic abstraction because it turns out that with other kinds of abstraction that we have, we can kind of really nicely get most of the same benefits at layer 2. So longer term ideas. So this is just kind of very far off. One of the previous slides I had also talks about how you can extend abstraction. So it's not just abstracting things at the user level, but it's also abstracting the aggregate signature algorithms that are used for at the beacon chain. And it turns out that that's possible in a way that we didn't realize initially. So that's something that we might want to introduce in a few years when we want to go quantum proof fully. In the future, possibly reduce the role of gas in the protocol. So this would basically mean that if we have a protocol where state transitions just get proven through Starks, through zero-knowledge proofs, then it doesn't really matter how complex the computation is because only one guy needs to do the computation. Once they do the computation, they prove it, everyone else verifies the proof. And so if you switch over to this paradigm, then the only real externalities are bandwidth and state storage, and with rent, state storage just becomes a kind of bandwidth, and so everything can be kind of measured in terms of bandwidth, which is just economically really elegant. We could write some of the kind of system components, so things like hibernation, waking, some of these other features that we talk about in WebAssembly code, and we can try upgrading them over time. We can try giving users kind of more choice of which of these kind of extra level layer utilities they use. Abstract the consensus layer even further. So there's definitely kind of more ways over time to try to kind of remove some of the assumptions that we currently have inside of Ethereum that reflect how Ethereum is kind of supposed to be used, and instead make it be this something much closer to this kind of general economic computing platform where all of the other logic itself can just be built as these kind of programming languages at higher levels on top. And what this means is basically that it just becomes much easier to upgrade the technology without having to make kind of frequent changes to the protocol, without having to rely on things like governance to decide exactly which option to use, because, well, you can have both options on top of the same protocol. And basically, you can continue to have kind of high rates of protocol and innovation on top of a more and more stable layer one. So, thank you.